So let's do a video here for, we said we were going to do some videos. We did the first law. Let's do Newton's second law of motion. So this is Newton's second law. And to state it quite simply, it is net force, which is the sum of all the forces. If you're not familiar with this symbol from math, sigma, and it means sum of, so the sum of all the forces, vector sum, this is a vector, add up all the forces acting on an object, and it will equal the mass of that object times that object's acceleration. So that's pretty much it. There's this about the simplest, shortest law there is, and it's the one you have to use quite a lot. So if you have some object, I don't care what it is, some wagon or something like that. Let's say we have a wagon, and you have all these different forces on it. You can have the force of the ground pushing up on it. You can have it force of it being pulled. You can have someone else trying to pull it the other way. You can have friction on the wheels on the ground. You have all these different forces, and you have the force of gravity pulling down it. You have all these forces, force 1, 2, 3, F4, whatever they happen to be. It's not important for this little example. We have all these forces acting on something. They can even be at angles, in which case you'd have to take components and stuff like that. But you have all these forces, and then you want to know what the object is going to do. You simply add up all of the forces that are acting on it, and then you set them equal to ma. And in fact, since this is a vector, a is an acceleration, it's a vector too, you actually have to break this up. So maybe let me make my example a little simpler just for the first one. Let's get rid of the vertical forces and only talk horizontally for the moment. We'll add those in later. Let me come back to them. So let's talk only the forces that are all parallel to each other. And what you would do is you would add them up. F2 plus F4 plus F5 equals ma. Okay, so you add them all up, all these vectors, they're all parallel, so you'll be able to add them just like scalars. But then you have to also be very careful about doing something like I just did. I'm just telling you, you add them up. But the one thing I didn't do while adding them up is pay attention to the direction they're going. Now this one's going to the right, and typically to the right we count as positive. That would make these two vectors negative. So what you'll want to do is you're going to use, you're just going to go ahead and put the negative as a subtraction. You're not going to try and hold it inside the variable. And so this would be F2 minus F4 minus F5. And you add them all up. You take the actual mass of the object, whatever it happens to be, and then it would tell you what the acceleration of the object would be. So you could imagine if this was one really strong kid pulling on it and then another, like say a couple other kids that weren't as strong pulling in the other way, but it turns out that they were all together the same strength, like this was a tug of war, and F2 equaled F4 plus F5, then we would get 0 and this would not be moving at all. Now if F4 and F5 were stronger than F2, then this acceleration would end up being negative because you'd have a smaller number minus two numbers that were bigger than it, and you'd get a negative acceleration and it would accelerate to the left. If F2 was stronger than F4 and F5 together, you'll end up with a positive number minus two smaller numbers, and you'll get this positive acceleration, and A would be positive. So the big thing to remember about this is basically just the way you go through and find it. Now before, I had written them and I erased them because I thought about it. Oops, sorry. And I had two other forces. So I had like some other force here, F3 and F4 acting on it. Now if we had that, oh, not F4, that was F1. Sorry, I already have an F4. So F1, if you have forces that are perpendicular, then what you have to do is you have to do one of these in the x direction. So this would be the x direction version. And then you'd have to do a y direction version. So this would be F1 in the positive direction minus F3 in the negative direction equals ma in the y direction. And then this one have to be the acceleration in the x direction. Because remember, acceleration is a vector, so we can have an x component and a y component. And so This would allow you then to solve these independently, and then you could put it all back together and get an overall motion of it. Okay? If the forces add up to 0, the acceleration is 0. If that's true, it's called a static problem or equilibrium. Static problem, there's static slash equilibrium problem. And that is in the case that all the forces add up to equal 0. Okay, so that's one you got to keep in mind. Equilibrium, all the forces are equaling out and it's not moving. And then, or static, it's unchanging, there's no acceleration to it. Just keep this in mind. If the net force is 0, does that mean it's not moving? Not necessarily. It just means the acceleration is 0. So if this object was moving at a constant speed in a straight line without turning or speeding up or slowing down, then the net force on it would be 0. So for example, if you're in your car and you're on the interstate and you're going 70 miles an hour and you're not speeding up or slowing down and you're just driving in a straight line, you're actually in equilibrium at that point. The total net force is 0. So the force of gravity pulling down on you and the ground pushing up on you and the force of the engine pushing you forward and the wind resistance trying to stop you, they all add up to 0, at which point you're not accelerating. And with the exception of if it was minor little bumps and stuff like that in the road where there's vibrations, you feel like you're moving. If you were on a perfectly smooth road, perfectly smooth where there was no bouncing or little vibrations at all, you wouldn't be able to tell you were moving, right? You would be in equilibrium, it would feel exactly the same, and everything would work exactly the same for you. All right, so that's Newton's second law. The best thing to do with this is just do a bunch of practice problems on this, do different forces, different ways. If you have forces that are at an angle, I guess I should throw that on there. Let's say you had one other force here that was at some angle. I don't care what angle, we can put it this way, and we'll call it F6, and we'll say it's at angle theta. Well, what you do with that is you have to take components of it. You'd have this component and this component. This would be F6 sine theta. That's that part right there. And this one down here, sorry, F6 cosine theta. Sorry, it got a little messy there. And then what you would have to do is add these on. So this would be minus, or I'm sorry, this is vertical. So plus F6 sine theta. And this one, it's in the negative direction, which would be minus F6 sine theta. So if you have something at an angle, you may have to take components of it and do something like that.